Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this chapter, chapter 5, we would like to continue in the detailed design of our absorption column, whether it is a plate tower or a pack tower. In chapter 4, we started by determining the diameter, and we said that the determination of the diameter of an absorption column is basically based on the fluid dynamics, and therefore we try to avoid flooding, and by avoiding the flooding we will determine the actual gas velocity inside the column, and therefore we can determine what is the diameter required to have that gas velocity. In this chapter we would like to talk about the determination of the height of the column. And the height of the column is based on mass transfer principles. It is somehow related to the diameter because diameter is going to determine the gas velocity, and the gas velocity is going to determine the interaction between the gas phase and the liquid stream. Now this interaction is going to determine the efficiency of the mass transfer operation, and therefore in a very in a high mass transfer rate, if we have a high mass transfer rate, then the column required will be shorter, the contact between the gas and phase will be shorter. And if we have a slow mass transfer rate, then obviously the contact between the gas stream and the liquid stream has to be longer. We are still using the same reference, chapter 5 of Principles and Modern Application of Mass Transfer Operations, and we will start with packed bed, then we will be talking about tray tower. So the height of a packed column refers to the depth of the packing material needed to accomplish the required removal efficiency. Obviously, the more difficult the separation, the larger the packing height required. So for example, a much larger packing height would be required to remove SO2 than to remove chlorine from an exhaust stream using water as the absorbent, because as we know, chlorine is more soluble in water than SO2. Determining the proper height of packing is really very important, since it's going to be affecting both the rate and efficiency of the absorption process. Now we need to keep in mind that when we talk about the height, we are talking about the height of the packed bed. We're not talking about the total height of the column. So when we're going to calculate the height, it's going to be only the height of the packed bed, and we need to keep in mind that at the top here we need to keep some distance for the gas to uniformly get to the outlet. So let's say something like a half a meter at the top, and the same thing a half a meter at the bottom, so that we can have a nice separation between the inlet gas and the outlet liquid. The other thing is we need to keep in mind that channeling. So in order to avoid channeling, we need to make sure that the height of the bed does not exceed 2 meters. So if it is more than 2 meters, then we need to add liquid collector and liquid redistributor, so that we can have a very nice wetting of the packing material from the liquid that is coming from the top to the bottom. So in calculating the total height of the column is going to be the height of the packed bed, which we will see how it's going to be calculated, plus half a meter at the top for a uniform gas release to the outlet, and half a meter at the bottom, so that we have a nice separation between the inlet gas and the outlet liquid. And if we have any redistributors at the bottom, in between, because the total height was more than 2 meters, and that the purpose of that is basically again to avoid channeling. Now there are a number of theoretical equations are used to predict the required packing height. These equations are based on mass transfer principles, and this is why We spent chapter 1 and chapter 2 in this course to talk about the molecular diffusion and the convective mass transfer principles. Now, depending on which phase is controlling the absorption process, either the overall gas mass transfer coefficient or the overall liquid phase mass transfer coefficient is going to be used as the starting point to derive an equation to predict the column height. And then a material balance is set up over a small different sections or heights of the column. Now, a general form of the design equation for a gas phase controlled resistant is given in this equation here. Now, keep in mind, we are designing an absorption column. We are choosing the solvent. So, more or less, we are confident that the solvent is going to be really, or the solute is going to be very or highly soluble in the solvent. This is why we chose the solvent. And therefore, we somehow confident that the controlling or the main resistance is going to be in the gas phase, not in the liquid phase. And this is why we will be using the overall gas phase transfer coefficient in an absorption process and the overall liquid phase mass transfer coefficient in a stripping process. So as you see in the equation is basically the total height of the packed bed is equal to the height of transfer units and the number of transfer units. And the idea here is basically in order to be able to determine the height of the packed bed, we can divide the bed theoretically into small sections, and these sections you can consider them to be similar to the number of stages we used to calculate in chapter 3, and also you can think of them like those in a tray tower where you have each tray is basically a stage by itself. Now they are theoretical because we know that we have continuous contact between the gas stream and the liquid stream in a packed bed. We don't have separations after each sections. So but they are going to be very helpful in calculating the height of the packed column. Now, the height of the packed column is basically the height of transfer units and number of transfer units. And these small sections are basically called the transfer units. We don't call them stages or trays. Trays are for tray tower, and the stages are basically when we talk about ideal number of stages or theoretical number of stages, but here we call them actual transfer units, so number of transfer units. Now the value for the height of each section, the height of transfer units that is used in designing the absorption system are usually from experimental data. And to ensure greatest accuracy, vendors, and vendors I mean manufacturers of absorption equipment, normally perform pilot plant studies to determine the height of the transfer units, HTU. For common absorption systems such as ammonia and water, or H2S in different kind of solvents, manufacturers have developed graphs for estimating the HTU, the height of transfer units. Now, these graphs do not provide the accuracy of pilot plant data, but they are less expensive and easier to use. Now, if you cannot get access to a pilot plant, or you don't have the necessary graph for your system, because those graphs are developed based on specific packing material, specific size of the packing material, and so on. So if you don't have the necessary graph for your specific system, then you can use this equation here to calculate the height of a transfer unit. The height of transfer unit is calculated by GMI over KYAH, where GMI is basically the gas phase molar velocity, and I have to emphasize here its molar velocity, which can be calculated by the gas molar flow rate divided by the column cross-sectional area. In chapter 4, we already know the diameter of the column, so it is so the cross-section area will be pi over 4 diameter of the column square. And the gas molar flow rate, we already know it from our mass balance calculation. And capital KYAH is basically the overall gas phase volumetric mass transfer coefficient. And in here I call it volumetric mass transfer coefficient because we are using the AH, which is the hydraulic specific surface area. We already know how we calculate capital KY, the overall mass transfer coefficient, by knowing KX, small kx and small ky, and the Henry's constant. And in the beginning of chapter 4, we learned how basically we use the correlations for specific packing material to calculate the small ky and the small kl. Keep in mind, in those correlations, we were calculating kl, small kl, not small kx. So we have to use the tables that we saw in chapter 3 to convert that value of kl into kx. Now, the number of transfer units, NTOG, NTOG, can be obtained experimentally again, or it can be calculated from using different methods. For the case where we have the solute concentration is low, which is basically a dilute solution, and this is basically a common situation in the oil and gas process, and the equilibrium line is basically a straight line, then this equation can be used to determine the number of transfer units based on the gas phase resistance. Now, as you see here, it's this equation here is more or less very similar to the Kremser equation, except that in Kremser equation, if you remember, there was ln 1 minus 1 over A. So the number of transfer unit is basically can be calculated using this equation. Now, if you look at this system here, you will see that if you remember, A is the absorption factor, which is L over mv, and again, absorption factor is basically relating to the gap between the operating line and the equilibrium line. So the larger the gap, the higher the value of A, and therefore there will be less number of stages required, less number of transfer units. Now we are talking about less number of transfer units required to achieve the target purity of the gas stream. Now, the opposite is true. The smaller the value of A, the absorption factor, then the smaller the gap between the operating line and the operating line, and therefore it's going to be larger number of transfer units required to achieve the target. In a case where we have really very soluble solute in the solvent, so we have Henry's constant is very close to 0, and if we are starting with a solvent that is basically pure, then we will have A is approaching 0, so this is 1 over 1, 1 minus 1. A is M is approaching 0, so A will be infinity value, and therefore 1 over infinity will be almost equal to 0, and therefore the number of transfer unit can be approximated equal to ln y1 over y2. x2 equal to 0, this is gone, so number of transfer unit will be equal to ln y1 over y2. And this is obviously only for the case where we have a very soluble solute in the solvent, and this is usually takes place when you have a reaction involved in the system. So once you calculate the number of transfer units, straightforward using the mass balance, and the height of transfer unit, again straightforward. You calculate the gas phase gas molar velocity and the overall gas phase volumetric mass transfer coefficient, then you can calculate the height of the packed bed. Height of the packed bed will be equal to the height of transfer units multiplied by the number of transfer units. Now remember, this is the height of the packed bed. You need to consider the top section, which is half a meter, bottom section half a meter, and if the height of the packed bed is more than 2 meters, then you have to divide it into multi-beds, and you need to include something like 30 centimeters or half a meter for liquid collector and liquid redistributor. And that is going to give you the overall height of the column. It's the same thing if you have a stripping section, stripping column, but in this case again, we are talking about we will be using the overall liquid phase mass transfer coefficient. And again, because in the stripping process, we know that the resistance is going to be in the liquid phase, not in the gas phase. So the total height will be the height of transfer units multiplied by the number of transfer units, but we call them overall height of a liquid phase transfer unit and the number of liquid phase transfer units, because the resistance is there. And the height of the liquid phase transfer unit will be the molar velocity of the liquid phase. So it's liquid molar flow rate divided by the column cross-section area. And capital KXAH is the overall liquid phase volumetric mass transfer coefficient. And in terms of number of transfer units, we will be using because this is the target, is basically to reduce the composition of the liquid phase from X2 to X1 using this solvent at this equilibrium constant. And capital A, again, it is the same, which is the slope of the operating line over the slope of the equilibrium line. This is basically to remind you of converting small kl into kx. Small kl, that is used using the correlations which we learned in the beginning of chapter 4, to small kx using xpm, and then we can go ahead and calculate the overall mass transfer coefficient.